Flock is used to applying numerical integration schemes on his computer. However, he never thought about how exactly it is possible for computers to perform numerical integration. Luckily, Leon is here to explain numerical integration methods, the Newton-Cotes formulas, as well as the trapezoidal and Simpson's rule. We start by assuming a general function f of x. Our goal is to calculate the integral over some interval ab of this function corresponding to the orange area. Instead of analytically integrate the function, however, we aim to estimate the orange area by adding together some function evaluations f of xi multiplied by some weights omega I. Before we get started with the hands-on mathematics, please consider leaving us a like or a comment. We are especially grateful for subscriptions and shares. Thank you very much. For the scheme we want to derive, we assume some function evaluations f of xy equals yi at some support points xi are known. An illustration of this situation is shown here. 5 values x1 to x5 between the points a and b are known. We further know the function evaluations f of xy at these points. A reasonable estimation of the function f of x in the interval ab is the lowest grade polynomial passing through all the points xi. This polynomial does always exist and is uniquely defined. The first challenge now is to find this polynomial. Luckily, a general method for finding these polynomials is well known and can be applied for our scheme. We use the Lagrange polynomials for estimating the function f of x as L of x, with L of x being the sum of the function evaluations yi multiplied by the Lagrange polynomials small li of x. To sum up what we just did, we approximated the function f of x with L of x, which again uses the Lagrange polynomials in order to define the lowest grade polynomial passing through all the points yi. The Lagrange polynomials look quite scary if one is not familiar with them. We recommend choosing 2 points and calculate the approximation at a hands-on example yourself. You will see that the calculation is not as scary as it seems. In order to derive our scheme, we now integrate L of x over the interval ab. The area A, which is equal to the desired integral, is approximated by integrating our function L of x. Using the linearity of the sum and the integral and considering the fact that yi does not depend on x, we can rearrange the equation as follows. Here we also multiplied and divided by the factor b minus a. This will come in handy very soon. Compare the equation we arrived at now to what defined as our goal in the beginning. The orange part corresponds to the weights omega I. However, these weights depend on the interval ab. Weights that are independent from the interval are more universally applicable. Suppose the substitution s defined as x minus a over b minus a. The resulting differential dx is then equal to b minus a times ds, with s being in the interval 0 to 1. Applying this substitution to our weights cancels not only the dependence on a and b, but also the term 1 divided by b minus a we introduced in the calculation above. We now finally arrive at a general, interval-independent term for the weights omega I. With this, we can now very elegantly derive the Newton-Cotes formulas. For the Newton-Cotes formulas, the support points xi are chosen to be equidistant, meaning that they are evenly spread over the interval ab. We distinguish open Newton-Cotes formulas, where the points a and b are not included, and closed ones, where the points a and b are included. Let's look at some closed Newton-Cotes formulas. Here, the points xi are calculated by simply adding I times the difference between any 2 points to the initial starting point a of the interval. The most famous Newton-Cotes formulas are the ones of lower degrees, with the closed Newton-Cotes formula comprising only 2 support points being known as the trapezoidal rule. Finally, let's now look at some important properties of these formulas. Newton-Cotes formulas integrate polynomials of up to degree n exactly, if n is uneven, and up to degree n plus 1 if n is even. Therefore, Newton-Cotes formulas with even n, such as the Simpson's rule, are preferred. The scheme becomes very calculation intensive and is unstable for higher n. This is why one does preferably use low degree Newton-Cotes formulas. In order to still be able to approximate integrals over bigger intervals, it is very common to split the main interval into subintervals and apply low degree Newton-Cotes formulas to these subintervals. This way one can assure convergence, stability, accuracy and calculation efficiency when evaluating some integrals. If you watched the video until now, thank you very much for sticking by, have fun calculating and see you next time.